Hi, this is OrgoChemSimplified, and today we're going to do a carbonyl mechanism problem. Okay, so we have this compound here, and we're asked, what's the mechanism that goes from here to here? Well, the only difference is we're exchanging one of the protons on this carbon with a bromine. So, whenever you have a mechanism problem, always start with, what's your starting material? What's it going to do? Okay, so we have this oxygen, this carbonyl oxygen, that's a functional group. So it could act as a base, right? We also have these protons here that are fairly acidic, but not too acidic. Okay, so what we want to do is look at what we're reacting it with. Okay, we have Br2, not basic at all, and ACOH, not basic at all. Okay, so ACOH is an acid. It functionally acts as an acid. Okay, so what did we say? We had this carbonyl oxygen, which can act as a base, and now we have ACOH, which can act as an acid. So that's probably what's going to happen. We're going to have the electrons on the carbonyl oxygen, and it's going to steal a proton from ACOH. I'll just write it as H+. It's effectively the same thing. So when we take that proton, that's going to activate the carbonyl. Okay? So it's going to activate the carbonyl. Next, what do we have now? Well, we just took the proton off ACOH, so now we have ACO minus. Right. We could take off this proton here. Well, first this OAC minus is going to act as a base, because it's not a very good nucleophile. So we know it's going to act as a base. Well, if we take this proton off, that's just going to go backwards. That's not going to progress ourselves forward. So the next thing we want to ask ourselves is, what's the next most acidic proton? And the next most acidic proton are the alpha protons. Now we're left with a choice, right? Do we take this proton off, or do we take this proton off? Well, this proton is less sterically hindered. It's more on the outside. It's going to allow the OAC minus more room to get in than this proton. So we're going to see more of this deprotonation step than the other deprotonation step. So once that occurs, these electrons are going to move up, and we're going to get rid of that positive charge, which is what we want. So it's kind of a chain reaction where this is deprotonated and all the electrons are being pushed upwards. So let's draw that compound. We get an OH and a double bond. Okay, so what kind of compound is this? This is an enol. This is an enol. And we know enols, well, first of all, if we have an alkene, we know in alkenes, the double bond can act as a nucleophile. Well, in enol, that's even more so, because this oxygen can push down these electrons, creating a carbonyl, which is more stable, and it can therefore push out these electrons, and it's going to be even more nucleophilic than an alkene. And what's the most electrophilic compound we have here? Br2. So it's going to attack a Br. This bond is going to break. And that's how we attach that Br to this carbon. So we draw the result of that. We're going to get this OH plus. So we're almost at our product. The only thing we need to do left is deprotonate that proton. And the most basic thing we have, well, we just eliminated off a Br minus. So Br minus is the most basic compound we have. So it's going to deprotonate that proton. And oxygen is going to take its electrons back, becoming neutral. And that's going to give us our product. So there you go. You just figure out what are the characteristics of the compounds, and you just work through the steps and asking yourself if each of the steps individually makes sense. Okay, so hopefully that helped. If you liked the video, if it helped you, please give us a thumbs up. If you have a question or comment, leave it below. Thanks for watching, guys.